Hello there, welcome back to our channel, and we are going to explain to you MOSFET differential amplifier using active load. So in our previous module, you see that we have used passive loads in the differential amplifier. Now, what is passive load? So right here, the transistors Q3 and the Q4 makes an active load for the circuit. So if we replace this network of Q3 and Q4 using simply resistors, then the circuit called as MOS differential amplifier, simply using passive load, or simply call it MOS differential amplifier. However, when we are using a current mirror technique, which we have explained in our previous modules, so using Q3 and Q4, we are providing the bias currents to the transistor circuit of Q1 and Q2. That's the differential pair. So that currents is basically active load. Using the active load, we are doing that. So we have this voltage source V plus, from which we derive the current I that is entering into the circuit. Now the transistor Q3 and Q4 are PMOS transistors because of the direction of the arrow. We see that the current flows from the source pins of the transistors. Let me write, these are the source pins, these are the gate pins of the transistors, and these are the drain pins of the transistor. So we say that the current is flowing from source to the drain based on the direction of the arrow, and they are PMOS transistors. Now the gate pin of the transistor Q3 is shorted with the drain pin of the transistor for the transistor Q3. That makes it a diode connected transistor. We call it that way. It's not exactly a PN junction diode, but we have the convention of saying that. But in case of BJT, if we use the current mirror, we implement this current mirror using BJT, which we have done in our previous modules, then we call them as a diode connector transistor, where base is shorted to the collector pin of the transistor. Now, what we get after doing this, if we short the gate and drain together, it makes sure that the transistor always operates in the saturation region, which is the region right to this line, where you have a constant current source. This is ID versus VDS. Okay, and that's how you have this VDS. So in this transistor, for transistor Q3, we see that the VGS will say that mod of VGS is equal to VDS is equal to that, right? So we say that, and VGS is equal to VDS, and VGS of the transistor 3 is equal to VGS of the transistor 4, because you see the gate is at the same potential here, and the sources of both the transistor are at the same potential, and the whatever the voltage appears at the gate after the circuit is turned on, there is an equal drop across the transistor. So we'll see that voltage is actually the voltage drop across source and gate here, and the voltage drop across source and gate here. So that is your VSG, here your VSG. We are taking a mod here, right? So understand that. Now this voltage drop is your positive and a negative. So we'll call it as a VSD. We are taking here VDS, the mod of it, and here also you have this drop VSD. And ideally, then we say that the voltage drop at this node is equal to the voltage drop at this node, the voltage potential actually. Okay, so we say that uh, VDS3 is equal to, let me write here, VDS3 is equal to VDS4. And this happens, this especially this the two conditions happens if the Q3 and Q4 are same. It means their threshold voltages are same, their structures and other intrinsic parameters and the properties are same. They're exactly a matched pair. When that happens, the current into the transistor, this current I, that is coming then to the source pin here. This is, let's say, your drain current. This is your source current. Here is also your drain current, and here is your source current. So if that is the same, then we say that ID3 is equal to ID4. This is a current mirroring technique where we just mirror the current in transistor Q3 into the transistor Q4, and that becomes the basis to provide the bias currents to the transistor Q1 and Q2, which is a differential pair. And then your ID1 here, this is your ID2, which are the current coming from the top. And again, you don't have a current going inside the gate pin of the transistor. So IG, current inside the gates of the transistor at 0. And then you have this source current IS2. This is IS1. So we'll say that ID1 is equal to ID2 is equal to ID, and IS1 is equal to IS2 is equal to IS. And Q1 and Q2 are NMOS transistors. So I have forgotten to draw the arrow here. So let me do that. So arrow, direction of the arrow indicates the current flows from the drain to source. Okay, here the direction of the current indicates the current flows from source to drain because they are complementary transistors. Q3 and Q4 are complementary to Q1 and Q2. Now, having said that, we come back to our topic, and these currents are coming here, and the I bias then becomes IS times 2 times the IS, right here, IS right here. And then you have this negative pin, negative voltage supply pin. That is how it works. Now, we see that the transistor Q3 are there, and Q3 operates in saturation region, and so is the Q4, and transistor Q1 and Q2 have to be also operated in the saturation region. The condition for operating the transistors in the saturation region is that the VDS minimum should be greater than VDS minimum should be greater than overdrive voltage of the transistor, and the V overdrive is the mod of VGS minus VTH in the MOSFET should be greater than or equal to V overdrive. Okay, so when that happens, your differential amplifier is ready to operate after setting up the bias points. And now you have this V in 1, and then you have this V in 2. You have positive and the negative inputs here. And based on that, you have output. So you have a positive going signal and then negative going signal. Output here would be like this, with, of course, the gain factor adding to that. If you have the negative going output here and then the positive going, the output is like here. So this is also a differential input, and single-ended output, single-ended output. Okay, is there anything left? We can also write the expression of the drain current in the saturation, and we also can write the expression of the drain current in the triode region. So I leave it as an exercise for you. And then for the given values of the voltage supplies, you and the bias current, let's say bias current is 1 milliampere and the voltages are like plus minus 3 volts. Accordingly, you can get the calculation for the V out. Okay, so you also can say that the V out here is going to be V plus minus this drop VSD or mod of, let's say, VDS. So that's how you get that situation and then get that voltage. Okay, so hope you like this video. Stay tuned for more information. Put some comments, like the video, subscribe to the channel, share it with others for wider reach. Wish you happy learning.